Welcome to our presentation on multi-way clustering in Stata, Theory and Practice. This session is specifically designed as a comprehensive guide for econometric students and researchers who are keen to understand and implement robust inference techniques for non-nested data structures. Throughout this presentation, we'll delve into the theoretical underpinnings of multi-way clustering, its practical application using the latest features in Stata 19, and the powerful reghdfe command. Our goal is to equip you with the knowledge to correctly apply these methods and accurately interpret your results. Let's begin by exploring why this advanced clustering technique is so crucial in empirical research. Consider a typical panel data scenario, analyzing wage determinants. Here, errors can be correlated along multiple dimensions. First, we have the firm dimension. Wages for workers within the same firm are likely correlated over time due to factors like company culture or management practices. Second, there's the year dimension. Wages across all firms in a specific year can be correlated due to macroeconomic shocks like a recession or high inflation. The poor problem is that standard one-way clustering can only account for one of these dimensions at a time, either firm or year, but not both. This failure to account for all correlation sources leads to standard errors that are artificially small, which in turn increases the risk of type 1 errors, or false positives. We might conclude a variable is significant when it actually isn't. In the diagram, worker A and worker B are correlated because they are in the same firm. Worker A and worker C are correlated because they are both affected by the 2024 inflation shock. Standard clustering might only capture the first link, ignoring the second. Given these complexities, how do we decide which clustering method is appropriate for our data? The next slide provides a helpful decision-making flowchart. This flowchart serves as a practical guide for selecting the appropriate standard error adjustment method for your econometric analysis. We begin by asking a fundamental question: are your observations independent? If the answer is yes, then you may only require robust standard errors to account for heteroscedasticity. However, if observations are not independent, indicating correlation within groups, we proceed to the next step. Next, we determine if this correlation exists along a single dimension or multiple dimensions. For a single dimension, a standard one-way cluster is often sufficient. If your data exhibits correlation across multiple dimensions, it's crucial to assess if these dimensions are nested. For instance, if students are nested within schools, you would simply cluster at the highest level, which is the school. If the dimensions are non-nested, such as firm and year effects, then multi-way clustering is required. However, this method relies on asymptotic theory, necessitating a sufficient number of clusters, ideally more than 30 to 50 per dimension. If you meet this requirement, you can proceed with multi-way clustering. If the cluster count is insufficient, the wild bootstrap is the recommended alternative for reliable inference. To effectively implement multi-way clustering and other robust inference techniques, it's crucial to select the appropriate Stata command. This slide provides an overview of the main tools in our toolkit. First, we have Stata's native regress and ivregress commands. As of Stata 19, these are excellent for general linear models and simple setups, as they now directly support multi-way clustering syntax. Second is the user-written reghdfe command by Sergio Correa. This is the gold standard for models with high-dimensional fixed effects, or HDFE, such as when you have thousands of firm fixed effects. It's extremely fast and efficiently handles massive datasets, even automatically dropping singleton observations. Third, for situations with a small number of clusters, typically fewer than 50, the boottest command by Rudman and others is essential. It performs a wild bootstrap, which provides more reliable inference when the asymptotic assumptions of standard methods don't hold. For example, if you are running a simple regression of wages on education with clustering by state and year, the native regress command in Stata 19 is perfect. But if your model includes fixed effects for every individual and every firm in a large dataset, reghdfe is the only practical choice. Let's take a closer look at the exciting new capabilities introduced in Stata 19. The mathematical foundation of multi-way clustering, as introduced by Cameron, Gelbach, and Miller in 2011, is based on a concept known as the inclusion-exclusion principle. The formula, often referred to as a sandwich estimator, essentially sums the variance matrices calculated for each clustering dimension individually. So we have vCluster1 and vCluster2, representing the variance components from each distinct clustering dimension. However, simply adding these up would lead to double counting the correlation that exists across both dimensions simultaneously. Think of it like a Venn diagram. If you sum two overlapping circles, the intersection gets counted twice. To correct for this double counting, we subtract the variance matrix of this intersection. This ensures we arrive at a single, correctly adjusted, robust variance estimate, providing a more accurate measure of uncertainty. This formula is powerful, but it relies on some important underlying assumptions. Let's examine those next. First, we have the asymptotics assumption, also known as the large G assumption. The standard errors are only consistent if the number of clusters in all dimensions grows sufficiently large. As a practical rule of thumb, aim for at least 30 to 50 clusters in your smallest clustering dimension. If, for instance, you're clustering by state and industry and only have 20 states, this assumption might be violated, suggesting a need for alternative methods like the wild bootstrap. Second, this method is specifically designed for non-nested structures. If your clusters exhibit a hierarchical, nested relationship, such as households within villages, applying multi-way clustering is incorrect. In these cases, you should simply cluster at the highest level of aggregation, like the village. Finally, we must consider singleton observations. These are groups containing only a single observation. Such groups do not contribute to variance estimation and can bias standard errors downward. Thankfully, the reghdfe command in Stata automatically identifies and drops these singletons, ensuring more accurate results. Now that we understand the theory and its requirements, let's see how applying multi-way clustering actually affects our regression results. A crucial point to remember is that clustering affects standard errors, not the point estimates themselves. The estimated coefficient, or beta, remains the same. Your estimated slope is still unbiased. Multi-way clustering typically increases the size of the standard errors because it accounts for more potential sources of correlation in the error term, introducing more uncertainty into our estimate. The direct implication is profound. A result that was statistically significant under a simpler model, like ordinary least squares, might become insignificant after applying multi-way clustering. This can fundamentally alter policy conclusions drawn from the analysis. For instance, an estimated effect might appear significant with narrow confidence intervals under OLS. However, once multi-way clustering is applied, acknowledging broader sources of correlation, the confidence interval can widen considerably, potentially leading to a loss of statistical significance at conventional levels. This shift highlights the importance of robust inference for accurate decision-making. A major update in Stata 19 is the native support for multi-way clustering within the VCE cluster option. Previously, users often had to create a combined group variable, for instance using eGenGroup, which was cumbersome. Now, you can simply list the clustering variables directly in the option. For a basic OLS model, the syntax is regress, VCE, cluster, var1, var2. This native support extends to other models as well, such as instrumental variables regression using ivregress with the 2SLS estimator. Additionally, Stata 19 provides various bias correction options, like the Hansen correction, that can be easily added to the command. In the code shown, regress ln wage tenure union VCE cluster ID code year directly tells Stata to perform two-way clustering by individual ID code and year. This is much cleaner than the old method of eGenGroup var equals group ID code year followed by VCE cluster group var. While their native commands are fantastic for many models, for complex fixed effects, another tool remains the top choice. Let's explore reghdfe. When your model includes high-dimensional fixed effects, for example, dummy variables for thousands of firms or individuals, reghdfe is the essential tool. It uses a method of alternating projections to absorb these effects without ever creating explicit dummy variables, making it incredibly fast and memory efficient, and correctly handles degrees of freedom. The syntax is straightforward. The main regressors are followed by the absorb option, where you list variables for fixed effects like fevar1 and fevar2. This effectively controls for unobserved heterogeneity. Crucially, the clustering variables are specified in the VCE cluster option to adjust standard errors for correlation. A vital distinction in syntax is that cluster A-B with a space indicates multi-way clustering, accounting for correlations within A and within B. In contrast, cluster A#B specifies one-way clustering on the unique interaction of A and B, treating each A-B pair as a single cluster, which is often a much stronger assumption. Before diving into estimation, it's crucial to properly prepare your data. We'll walk through 4 essential steps. First, you need to identify your data structure. Use commands like describe to understand variable types and xtset to formally declare your panel data structure, which is critical for time series and panel analyses. Second, and vitally important for multi-way clustering, check your cluster counts. Commands like unique or tab help you count distinct entities in each clustering dimension. Remember, you generally need more than 30 to 50 clusters per dimension to ensure the asymptotic assumptions hold. Third, verify that your clustering dimensions are non-nested. For example, students are nested within schools, so you would only cluster by school. However, industries and years are typically non-nested, making them suitable for multi-way clustering. Finally, generating groups using EGen group ID equals group var1, var2 is an optional step, primarily useful for creating unique identifiers if you're working with older Stata commands or need specific data manipulations. With these preparatory steps complete, we can move on to applying them in a practical case study using a well-known dataset. We will now walk through a practical example using the NLW work dataset, which is built into Stata, specifically from the National Longitudinal Survey of Young Women. Our objective is to estimate the effect of job tenure and union membership on the natural log of wages, ln wage. This data has a clear multidimensional structure. We need to account for correlations both within each person over time, using ID code as a cluster, and for common economic shocks across all individuals in a given year, using year as another cluster. The Stata code shown loads the data and provides a summary. We observe over 28,000 observations, with 4,711 unique individuals and 15 unique years. While the large number of individuals is robust, the smaller count of 15 years is something we'll need to address carefully later. A researcher might hypothesize that union membership increases wages. However, if union members are concentrated in specific firms or are more affected by year-specific economic trends, failing to cluster by both person and year could lead to an incorrect conclusion about the union wage premium. Let's begin the analysis with some baseline models to see how the standard errors change as we add layers of complexity. First, we run Model A, a naive OLS regression using heteroscedasticity robust standard errors. As you can see, the standard error for the union coefficient is very small, at just 0.004. Next, in Model B, we improve our model by accounting for the fact that observations for the same person are correlated over time. We use one-way clustering by the individual identifier, ID code. It's important to note that the point estimate for union remains identical, at 0.168, as clustering only affects the standard errors, not the coefficients. However, the standard error for union jumps dramatically from 0.004 to 0.012. This is a significant threefold increase, clearly illustrating how much within-person correlation was initially unaddressed, and how naive OLS was severely understating the true uncertainty in our estimate. This initial step already shows the danger of ignoring such correlations. But we've only accounted for one dimension of correlation. Now, let's move on to implementing full multi-way clustering to also account for time shocks. In this second step, we fully implement multi-way clustering. We use the reghdfe command, specifying both ID code and year in the absorb option to control for high-dimensional fixed effects. Simultaneously, we use VCE cluster ID code year to perform two-way clustering. The output clearly shows 4,142 clusters for individuals and 15 for years. It's crucial to note that reghdfe automatically drops 556 singleton observations, ensuring our standard error calculations remain unbiased. Now, observe the union coefficient. It has shifted to 0.145. More importantly, the standard error for union has increased again, from 0.012 in our one-way clustering model to 0.014. This further increase confirms that we are now effectively accounting for year-specific shocks that influence all individuals, providing a more robust and accurate measure of uncertainty. This demonstrates how fully accounting for both individual and time correlations expands our confidence intervals, giving us a more realistic picture of the precision of our estimates. However, with only 15-year clusters, we need to consider potential issues with small cluster counts. When the number of clusters in any dimension is low, typically below 30, the asymptotic theory that underpins standard cluster robust standard errors can break down, leading to inaccurate p-values. This is precisely the situation we faced with our 15-year clusters in the previous step, which fell below the recommended threshold. To address this, we turn to the wild bootstrap, a resampling method specifically designed to provide more reliable inference in such few cluster scenarios. First, you'll need to install the bootstrap command in Stata using ssc install bootstrap. After running your main regression, you can then apply bootstrap to the coefficient of interest, as shown in the code. The output provides a bootstrapped p-value. In this example, we see a p-value of 0.064. This value, being higher than the conventional 0.05, suggests that our result might not be statistically significant at the 5% level, which is a crucial change from what asymptotic methods might imply. For very small cluster counts, particularly below 15, it is recommended to use the weight web option, which ensures sufficient variation during the bootstrapping process. When presenting your regression results with multi-way clustering, there are a few critical points to consider. First, always perform a diagnostic check. It's possible for the variance-covariance matrix to become non-positive semi-definite, a technical issue. Fortunately, both Stata19 and the reghdfe command automatically handle this by applying the Cameron, Gelbach, and Miller adjustment. Beyond diagnostics, transparent reporting is key. You must clearly state the estimated coefficients, the cluster robust standard errors, and, crucially, the number of clusters for each dimension used in your analysis. As the example on the right demonstrates, this involves specifying the model type, detailing the clustering dimensions such as individual, n equals 4,142, and year, n equals 15, and explaining that this accounts for serial correlation and common time shocks. Finally, present your findings clearly, like stating that the effective unions remain significant at the 5% level with a p-value of 0.04. This comprehensive approach ensures the credibility and reproducibility of your research. To summarize our discussion on multi-way clustering, here are 5 key best practices to ensure robust and reliable inference. First and foremost, always meticulously check your cluster counts. It's crucial to have more than 30 to 50 clusters per dimension for the asymptotic theory underlying standard cluster robust standard errors to be valid. Second, for simpler models that don't involve high-dimensional fixed effects, leverage the new Stata19 native syntax. Specifying VCE cluster AB is now the most straightforward and efficient method. Third, when dealing with models containing high-dimensional fixed effects or extremely large datasets, reghdfe remains the gold standard. Its efficiency in absorbing fixed effects makes it indispensable for speed and accuracy. Fourth, if your number of clusters in any dimension is small, typically below 30, you must employ a bootstrap method like bootstrap to obtain valid p-values and prevent misleading conclusions. Finally, when faced with uncertainty about the precise correlation structure, always err on the side of caution. Be conservative and cluster at the broader, more aggregated level that is most likely to capture the underlying dependencies in your data. This approach helps ensure your standard errors are not artificially small. Before we conclude, here are some key references for those who wish to delve deeper into multi-way clustering. The foundational work by Cameron, Gelbach, and Miller from 2011 is crucial for understanding the theory of robust inference with multi-way clustering, as we discussed when explaining the inclusion-exclusion principle. Sergio Correa's 2016 paper introduces reghdfe, the highly efficient command for linear models with high-dimensional fixed effects that we highlighted as a gold standard for large datasets. McKinnon's 2021 work provides a guide to cluster-robust inference using methods like the wild bootstrap, which is essential when dealing with a small number of clusters. Finally, StataCorp's upcoming Stata19 and StataNow updates offer even more VCE options for linear models, further simplifying multi-way clustering implementation directly within native commands. These resources provide excellent avenues for further study and practical application of the concepts we've covered today.